Hello everyone and welcome to this first lecture. So today we are going to talk about collaborative automation. So let's try to understand what we mean by collaborative automation and why it is so relevant. Well, according to this report from McKinsey Company, manufacturing activities have 60% of automation potential, which means that the remaining 40% cannot be automated because either it is so expensive or it is so difficult. So nowadays we have two possibilities for example, an assembly task. So one is completely manual. So of course you have a small investment, a small productivity, but a very high flexibility. In turn, we might have a hard automation solution where you have, of course, a high productivity, but of course, due to the very high investment, but of course, a very non-flexible solution. Well, the novel solution is the one here in the middle. So it's an intermediate solution where we add a robot to the manufacturing workstation, which has been previously completely manual. So to achieve medium to high productivity and medium to high flexibility, still adding a small investment with respect to a completely manual workstation. So let's try to focus on one example. So here we have a completely manual station, and here you see the red arrows that exemplify the workflow of the process. And there are four activities, while the blue and the black are activities with low added value and very easy or cheap to automate. While the yellow and the red are activities with a high added value and are difficult or typically costly to automate. So we want to switch from this situation to a situation where 50% actually of the overall activities are going to be automated through a collaborative robotic application. So the collaborative robot will be responsible for the activities with low added value, which are the blue and black ones. Well, still the human operator will be responsible for the other two, so where we have high added value. And of course, those are typically more difficult to be automated. So let's have a look at the opportunity that we have by implementing this scenario. So let's focus on the manual workstation, which is the previous situation. So here we have accumulated earning, which is the margin that we have for each product times the number of products that we are going to produce in one-time unit. Of course, if we add some robotic manipulators, so the human and the robot will work in parallel, so we expect some increase in terms of number of products per each time unit. So we are going to identify this speed up in terms of throughput by this parameter s, and so we expect to have 1 plus s times p products to be produced in one time unit instead of simply p as in the manual workstation. And of course we have the same margin per each product, but of course we had to have a small investment which we identify with I. So the cumulated earnings is M times P times 1 plus S, where S is again the speed up in terms of productivity, and of course minus the investment. So if we compare the two and we compute the break-even, so what we get is that the break-even is P, number of products, equal to 1 over S times M. So we have the situation which is sketched there on the right, where we have, of course, a payback time in terms of units that have to be produced that highly depend on the margins that we have. Of course, the higher the margin, the shorter the payback time, but of course, the higher the speed up, the smaller the payback time. In this video, you see an example of this kind of concept of collaborative automation. So there's a human operator that is standing in front of a robot and they are coordinating each other so to assemble this whole part. Particularly interesting is how the coordination between the two is actually achieved. So let's have a deeper look on that. Well, in this picture, you see the typical architecture for now in industrial automation solution. So you have signals coming from the field, and of course those signals are stored in some register, and then there are Boolean expressions to allow transitions of a state machine to take different actions on the plant, and then of course the current action is then forwarded to the plant for the execution. Well, the plan is now a collaborative automation solution, so we expect to have both humans and robots. And of course, we can clearly understand that signals coming from the robot can be processed in the same way we were used to. But how about the human? Well, with some kind of vision system, we can take a picture on the environment and clearly identify where the human is in the picture, and so where he or she is with respect to the robot, and what the human is doing in this particular time instant. So in this picture here, you see a human operator that is using a nut runner. So for example, we can feed an artificial intelligence algorithm to understand what's going on within the scene. So, and that it is based on a human digital twin and an object digital twin. So by relating the two, we can clearly understand what's going on in this picture, and in particular, we can associate the kind of action that the human operator is performing. So in this example, the artificial intelligence is responsible for saying that at this current moment, the operator is using a nut runner. And that's a situation that can be simply considered as an additional signal that is now coming from the artificial intelligence rather than coming from a hardware device on the field. So based on these ideas, a couple of years ago, we decided to create a startup company which is called Smart Robots that is producing that device, which is a sort of some smart camera that see the scene and try to understand what's going on exactly in the same way that we have seen in the previous example. So in the next video, you will see an actual demonstration using the smart robot device that has been taken from demonstration at CES 2020. So I hope you enjoyed this lecture, and let's see you next time.